Dr. Ranjani Parthasarathi is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published paper in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on networks. This is lecture number 15. We have been looking at MAC protocols. In today's topic we will be dealing with the token ring protocol. In the token ring protocol, the FDDI standard is what we will be looking at today. So we will just take a quick look at what we mean by a token ring, a quick recap of what we mean by a token ring protocol. So in a token ring protocol you have nodes which are connected by means of links. So the nodes are connected in the form of a ring. So this is the ring setup that we have, and in this ring setup we have something called a token which keeps travelling along the ring, and if there is any node wants to transmit data, it basically grabs that token and then transmits the data. So if there is nobody transmitting any data, then the token is just circulating along the ring. Now, so let us say station A captures the token and sends its data to D. Okay. So the data that is meant for D will be going on the ring. When that frame passes by the station D, D will copy the contents of that particular frame, and it will just send the frame along. After it has copied the frame, it sends the data back to the ring, and then station A will receive that frame and it will release the token. So once A has released the token, any other station which has to now transmit data can transmit the data by grabbing the token. So this is the idea that is used in the token ring protocol. We have already looked at the 802.5 protocol, the 802.5 standard which is used for token ring protocols. FDDI is another standard that we will be looking at today. Before we take a look at FDDI, let us just do a quick recap of the properties of 802.5. 802.5 basically is meant to provide high throughput under heavy loads. Under low loads it does not give very good throughput. Second is, it also attempts to provide a deterministic bound on delay, and it has support for priorities in traffic. It has two options. It can work either based on the early token release mechanism or the delayed token release mechanism. Now when priorities are used, when a priority based mechanism is used, reservation needs to be done on a data frame, and only on receiving the reserved frame will the token be released. This obviously means that we need to use a delayed token release mechanism, and this again puts a dent on the throughput that can be achieved. So it is basically to take care of some of these problems and the necessity to connect up larger networks that FDDI has come up. So let us just, before we take a look at FDDI, a quick look at the throughput that can actually be achieved on 802.5. Now 802.5's throughput is closely related to the time it takes for the token to come back to a particular node, because remember that only when I get back the token I can transmit more data. So if I have transmitted some data and I have released the token, I have to wait for the token to come back to me. So time it takes for the token to come back to me, that is what we call as the token rotation time. This token rotation time is what determines how much of data can be transmitted in an overall fashion. So let us take an example. So let us say I have a 16 megabits per second token ring network with 200 nodes and 500 meters of cable. Suppose each node grabs the token and transmits a maximal 18,200 byte frame. In this case, let us try to calculate the time taken for the token to come back to node number 1 using early token release. The token rotation time will be equal to time it takes for the transmission to happen, that is 200 nodes are transmitting, each one transmits for some transmission time, which is calculated as the number of bytes that it transmits divided by the rate at which the transmission is taking place. So if you are transmitting at 2 megabyte per second, 18,200 bytes, 18,200 by 2 MB per second will give you your transmission time, into 200 gives me the time that it takes for the data to be transmitted, plus the propagation delay of the token around the ring. Now the ring is 500 meters long, so I divided by the speed of the signal transfer, being the signal that is propagating along the link. Now and if you look at it as UTP cable, copper cable, the speed of data transmission on copper cables is about 65% of the transmission speed of light, the speed of light. So therefore you say 0.65 into C, C refers to speed of light. So 500 meters divided by 0.65 C will give me the ring latency or the propagation delay. So 200 times transmission time plus ring latency, which works at about 1.82 seconds, is the total time that it takes. This is the token rotation time, the time that I get back the token after I have transmitted some data. So now this you can see can be too slow. So what is normally done in 802.5 itself is that you put a limit on the token rotation time. So all the stations agree on what's called as a token holding time. The purpose of the token holding time is to make sure that no token will transmit for too long a time. So token holding time is the longest time that a station can continue to hold the token. This determines how much data a station can send. So let us understand this by completing with an example. For example, let us say we have a 16 megabit per second token ring and they have agreed on a token holding time THT of 0.001 second. So let us look at how much data each station can send. A station can send up to 0.001 second into 16 Mbps, that is THT, that is the amount of time for which it can transmit at that rate and at a rate of 16 megabit per second. So you totally get a data transmit, again the amount of data as 16,000 bits, which is 2 kilobytes. So every time a station gets the token, it can transmit up to 2 kilobytes of data. Now this 2 kilobytes of data it can send as one large frame or it can send it as several small frames. Of course, you will have to send it as at least the as a standard size frame, because 2 kilo okay, in this case, since the 2 kilobyte frame you may be able to hold it in a one frame, but if you are looking at a large THT, then it may be possible that you will actually be sending several smaller frames instead of sending one large frame. Also remember that in each data frame of 802.5 you only have about 1500 bytes that can be transmitted. So given that only 1500 bytes can be transmitted, you will split the data into multiple frames and transmit. So either several small frames or one large frame, but the total time that you can hold the token is only your THT. So that is how the THT is determined and how it is used. So if you look at this token holding time, now you can see that this token holding time will put a bound on the token rotation time. Now how does that happen? The total token rotation time now you can see will be less than or equal to the THT, the token holding time, into the number of nodes. That is, each node holds it for THT amount of time. So THT into the number of nodes will give me the total time for which the transmission will take place, plus of course the ring latency. So this gives me the token rotation time. Okay. Usually only a small number of stations want to send data at any time. So the THT can be larger than the worst case. Though you have chosen a particular value of THT based on the fact that all stations could be transmitting, but if only a few stations are transmitting, then the THT will be larger than the worst case. The THT that you actually have could be larger than the worst case. Now, the token ring protocol adjusts the value of THT dynamically to maintain a reasonable TRT. So you want to make sure that this TRT is at a reasonable level, so that all the stations are able to transmit some data within a reasonable amount of time. So this is how the 802.5 protocol adjusts its token rotation time and so on. So now we will take a look at the FDDI protocol. We can see that there are a lot of things which will be different on the FDDI protocol. So we will focus on those differences. Most of the things are common, but we just focus on the differences. So if you look at the FDDI protocol, now FDDI itself stands for Fiber Distributed Data Interface. Now it is a token ring protocol, a token ring network, which is designed for reliable LAN or WAN use. Note that we are moving from LAN to WAN when we talk of an FDDI protocol. Typically a token ring, an 802.5 token ring protocol is used only in the LAN scenario, but FDDI is also meant for a WAN scenario, a wide area network scenario. So which means we are talking about larger distances. Okay. So it can transmit typically at 100 megabit per second data transfer using fiber optic cable or using UTP. Now if you use fiber optic cable, segment lengths are typically 2 kilometers, and the signaling that is used is we use a 4B 5B encoding technique plus the NRZI, the non-return to zero encoding technique. If you use UTP cables, then the segment length is restricted to 100 meters and we use the MLT3 signaling technique. So these are the two options that are available for setting up an FDDI kind of a network. And up to 500 stations could be transmitted, which means you can go up to 100 kilometers. So now you can see why we refer to this as a standard which can be used for a wide area network. Up to 100 kilometer network can be set up using the FDDI framework. Now if you look at the FDDI interface in terms of how physically the network is actually connected, let us look at what we have here. FDDI basically has two rings oriented in opposite directions. In normal operation only one ring is used. So we talk about what is called as a dual ring scenario. That is, between the stations you have a ring like setup, but you have two rings which are running between the different stations. One is called the primary ring, the other is called the secondary ring. In normal operation only one ring is used. So, the second ring is basically provided for fault tolerance purposes. Okay. Now, the reason why this kind of a mechanism is used is again because of the fact that FDDI is meant for larger networks, and the kind of network connection that is used in 802.5 protocols does not work out to be economical in the case of FDDI. So, to provide fault tolerance, it is better to have a redundant ring running rather than try to provide a scenario as you have in the case of 802.5 protocol. In 802.5, remember that you may have a central access unit and you will have different nodes connecting up to this access unit. Now, since the overall span of the network is much larger, of the order of about 100 kilometers, so it is impossible for you to have lines running like that from each of these nodes to a central unit. So, it makes better sense to have this kind of a ring structure. So, that is what is used. Now, the token or the data frame will circulate in the ring. Now, each station can buffer about 9 to 80 bits. Again, look, you can see that this is different from the 802.5 protocol. In the 802.5 protocol, each station typically buffers only 1 bit of data. So, it just looks at 1 bit of data, examines that and passes it along. Whereas, in the case of FDDI, each station can buffer anywhere from 9 to 80 bits of data. Okay. So, what is the purpose of this dual ring? We said the purpose was to provide fault tolerance. So, if a damage happens, let us look at what is done. So, if a cable or a node is damaged, the second cable is used to re-establish the loop. Okay. So, you can see what is happening here. So, let us say between this node and this node the link is cut. So, what we do is this end of one particular ring and the other end of the ring. So, we have two rings now, right. This is now both the rings you can see are cut. So, what we are actually doing is just looping this back over here at this station, similarly providing a looping back at this station. So, now you can see that starting from the inner ring, if I start from the inner ring, from here it is connected back like this and then it goes back to this node, this node, this node, again we find there is a loop back over here and then again these nodes are connected back like this. And finally, you can see that the ring is re-established. All the stations now are reconnected in the ring. So, that is the ring was disconnected, now you have made sure that it is reconnected again. So, re-establishment of the ring is what is done by means of this dual ring operation, in this dual ring operation. Okay. So, let us look at how these stations actually now get attached. Here again we have what is called as a dual attachment stations which are available. So, that is, this is a mechanism by which nodes are attached to both rings. So, a DAS interface, a dual attachment station interface, includes circuitry to use either ring for input and output. So, you have circuitry which will allow you to do that. You also have another option which is called as a single attachment station. So, in a single attachment station, this is something which is used on smaller networks. So, here what we do is we use a node may be attached to only one ring via a concentrator to reduce the interface cost. So, the concentrator contains an optical bypass to remove a SAS node if it fails. Note that this is very similar to the 802.5 setup. So, this is used only when the network is not as big as in the case of a WAN network, but it is used in other cases. So, look at the situation that you have here, you have what are called these SAS or the single attachment stations. These are connected by means of optical fibers to a concentrator. You have an upstream neighbor on this side and a downstream neighbor on the other side, and you will have options available at the concentrator to optically bypass or remove a SAS node if it fails. So, just as we had a relay in the case of 802.5, here you have an optical bypass to remove a SAS node if it fails. So, we have two options of connecting in the FDDI mechanism. Okay. So, if you look at the operation of FDDI, one of the choices that we had in the 802.5 was choice between early token release and delay token release. In the case of FDDI, we go for early token release. So, let us look at what happens in early token release. In early token release, a sender generates a new token as soon as he finishes sending his frame. Since FDDI rings can be up to 100 kilometers, this is needed to achieve good utilization. That is, the delay token release will not work out well for the FDDI protocol. It may work well for the 802.5 but not for the FDDI protocol. So, we go for early token release as the token release mechanism in FDDI protocol. We will take a small break and come back and continue on FDDI. Welcome back after the break. So, we have been looking at the FDDI protocol and we are just looking at which of the two token release mechanisms is more suitable for the FDDI. So, we said that early token release is more suitable for the FDDI protocol. So, in early token release what happens is that a sender generates a new token as soon as he finishes sending his frame. Since FDDI rings can be up to 100 kilometers, we said this is needed to achieve good utilization. Okay. So, the destination host copies the frame and sets the 2 bits in the trailer, but does not remove the frame from the network. So, the same that is pretty similar to what happens in the 802.5 protocol as well. So, as we said, early release always helps to improve the throughput. So, another station can seize the token and insert his own frame after the first sender's frame. So, second station also releases the token early, so other stations can transmit, tailgate, and the ring can be well utilized. Okay. Now, coming to the ring size and latency of the FDDI protocol mechanism, as we said, an FDDI ring can be up to 100 kilometers long. So, the ring latency is a significant factor on such large links. Since the ring is very long, we need to consider the ring latency. Okay. And we also said that each station buffers 9 to 80 bits of frame as it passes by, but it may retransmit bits before its buffer is full. Okay. But given that it can buffer up to 9 to 8 bits of frame, it essentially means that every station actually is adding to the ring latency, that is, it is adding to the delay in the process, in the passing of the data, in propagating the frame along the network. So, there is also a delay that is added by means of this buffering mechanism. So, we need to consider this delay as well as the already large ring latency when you are looking at the throughput of an FDDI network. And so, let us look at how that is done. Each station buffers from 9 to 80 bits of a frame as it passes by, but may retransmit bits before its buffer is full. So, what we have here is there is a delay that is added by each station. Each station has a delay because of this buffering of data that it is doing. In addition to this, we already have the ring latency. So, we need to consider both these factors when we calculate the ring latency. So, let us look at how that is done. So, if you look at the ring latency, we need to first consider the propagation delay. So, the propagation delay in a 1 kilometer cable, and if you are using again UTP cable, it will be 0.67 times C will be the propagation speed. So, 1 kilometer divided by 0.67 C will give me 5 microseconds per kilometer. Okay. So, suppose each node buffers 5 bits on an average. We are just assuming that on an average they are buffering 5 bits. So, the delay in the node will work out to 5 divided by 100 megabit per second. So, a 50 nanosecond delay that is introduced for this buffering. Okay. Now, for a network with 40 nodes and 10 kilometers of cable, let us look at what the ring latency will be. It will be equal to 40 into 50 nanoseconds. Why does this come about? Every node, there are 40 nodes, each node is introducing a delay of 50 nanoseconds. So, 40 into 50 nanoseconds delay because of the delay introduced by the nodes plus the actual ring latency that is due to the length of the cable. Length of the cable we said is 10 kilometers. Per kilometer you are getting a 5 microseconds delay. So, you have 10 into 5 microseconds, 50 microseconds plus 40 into 50. So, it works out to about 52 microseconds. So, you have a 52 microsecond ring latency for a cable of for a 10 kilometer ring. So, now let us look at the FDDI frame format. You can see that many factors are very similar to what we have in the 802.5 frame format. For instance, if you look at the token frame again is a 3 byte frame. You have a starting delimiter, you have the frame control field, and then you have the ending delimiter. Okay. If you look at the data format, you have the starting delimiter, then you have the frame control field, then you have a destination address, a source address. Remember that in the 802.5 we had one more field over here. Now, that is the access control and a frame control. Now, both are combined into a single frame control field in the token ring in the FDDI token ring mechanism. You have a destination address field 6 bytes again, source address field 6 bytes. Data can be from 0 to 4500 bytes. This is followed by a 4 byte CRC, the 32 bit CRC mechanism used for error checking, and then we have the ending delimiter which is half a byte, and you have a frame status byte which is 1.5 bytes. So, you have 12 bits for this and 4 bits for this. So, this is what the frame format in an FDDI protocol looks like. If we look at the frame control field, now remember that this is again a very important field because this is the one that distinguishes between a token frame and a data frame and has additional information about what kind of data is carried in this. Now, here you can see that there are 4 subfields here. We have the C bit which indicates the class of data that is being transmitted. Okay. Here we talk about something called a synchronous or asynchronous class of data. Then you have an L field which specifies the address length. Now, in FDDI you actually have an option of using either 16-bit addresses or 48-bit addresses. So whether we use 16-bit addresses or 48-bit addresses is specified by means of this option field, the address length field over here. So 0 indicates 16 bits, 1 indicates 48 bits and so on. Then you have an FT or the frame type field which indicates what is the type of the frame, and then you have a type field which is a control field which basically gives you the control type. Okay. So the frame type plus the control type will identify what kind of data is actually carried in this. Now we come back to this class field. We said we have two classes of traffic basically, synchronous or asynchronous traffic. So each frame can either carry synchronous type of traffic or asynchronous type of traffic. Now we will come to what we mean actually by the synchronous and asynchronous type of traffic. Okay. So what happens here is synchronous traffic is something which has basically been introduced to support delay sensitive traffic, particularly voice. So what we mean by synchronous traffic is that every time that the station gets the token, it can always transmit this synchronous traffic. Asynchronous traffic is something that will get to transmit only if it is given some extra time or if it has some slack time that is available. Okay. So now what is the synchronous and asynchronous? How is it different from the mechanism that we had in the 802.5 protocol? Remember that in 802.5 protocol we supported different priorities of traffic. We had different priorities for the data that could be transmitted, and each station could specify the priority and get the token earlier if it had some data that needed to be transmitted of higher priority. Now, but this priority based mechanism, remember, used the delayed token release mechanism because it was dependent on the delayed token release mechanism. Now in the FDDI we do not use delayed token release, we only use the early token release mechanism because that is what will be better for the early in the FDDI protocol. So given that we can't use priorities and reservations so on, we need a different mechanism for handling data of different priorities or different types. So this is where the synchronous versus asynchronous has been introduced in the FDDI protocol. So we just have two classes of traffic, synchronous and asynchronous. So synchronous is used for delay sensitive traffic, asynchronous is used for all other types of traffic. So that is the idea that we use. So synchronous frames are typically small, and that is up to 96 bytes of circuit switch data or 16 bytes of non-circuit switch data. So this is what we do. So normally what is done is you make sure that, I mean, synchronous traffic, if you are looking at voice being generated, 8000 frames would be generated per second. Okay, so which is basically to say that you want to support digitized voice. So given that I am using PCM transmission for voice, you would have about 8000 frames transmitted per second. So if that is the rate at which data is generated, you want to make sure that in the synchronous frame mechanism you are able to transmit that much of data every second. So a provision for transmitting at least that much amount of data has to be given for every station that is there in the network. Okay. So in synchronous frames, how is it that we handle it? Multiple stations may acquire a time slot or slots in the same synchronous frame, and once acquired a station receives the same time slot in every synchronous frame of the series until it explicitly releases it. That is, you have a guaranteed bandwidth. And synchronous frame generation does not wait for token. In asynchronous frames, what we do is they are normal data frames, and this can contain up to 4500 bytes of data. A station must wait for the token before sending an asynchronous frame. Okay. So sending asynchronous frames happens, the amount of data a station can send is limited by a maximum token holding time, which is determined by how late or early the token arrives. So when you release the token, you start timing and see when the token gets back to you. So the token comes back early, we say that the token has arrived early, then you get to transmit asynchronous frames. If the token arrives late, then you cannot transmit asynchronous frames, you can only transmit synchronous frames. This is the mechanism that is used. So when the token arrives, the measured token rotation time is compared with the agreed upon target token rotation time to determine if a station can send any asynchronous frames. So you have two terms that we use over here. We have something called a token rotation time and we have something called a target token rotation time. Now token rotation time is something that we already are familiar with. We know how to calculate the token rotation time, the time it takes for the token to come back to you. Now target token rotation time is the expected time within which you expect the token to come back to you. Okay, so this is which is what we call as the target token rotation time. So if the token comes back to you within this target token rotation time, we say it's come in early. If it comes later than this, we say it has come in late. That's the idea that is used for determining whether you get to transmit asynchronous frames or not. So if you look at the token rotation time for a sample scenario, so let's look at this case. Let's say I have an FDDI ring which contains 500 stations and 100 kilometers of fiber optic cable. Suppose each station grabs the token and transmits a 1000 byte frame. So, the time taken for the token to come back to the node is, again token rotation time is calculated as 500 into transmission time plus ring latency. So, you talk about 500 into 1000 into 8 by 100 megabit per second plus 10,000, 100,000 meters, which is 100 kilometers, divided by the speed of light, which comes to about 40 milliseconds, which again is too slow. To limit the token rotation time, the stations agree on this target token rotation time. Okay. So, here the TTRT and the observed TRT will determine how long the station can transmit, and that time is called as the token holding time, the THT. So, what we do here is a station also keeps track of the time it uses to send the synchronous data, which is called its synchronous allocation or SA. Okay. So, when a token arrives, the station checks. What does it check? If the TRT plus the SA is greater than the TTRT, that is, including my synchronous allocation time, am I exceeding the TTRT or not? So, the token has come back to me within a particular amount of time, that is my calculated TRT. Along with this calculated TRT, I also add the time that it takes for me to transmit my synchronous data. This is my synchronous allocation. So, my TRT plus SA is greater than TTRT. This is my target token rotation time. If TRT plus SA is greater than TTRT, then the station does not send any asynchronous frames. But if TRT plus SA is less than TTRT, then the station may transmit data for a time up to a THT, which is equal to TTRT minus TRT minus SA. What do we mean by this? The difference between the TTRT and the TRT plus SA, that is the additional time that is available to me. That amount of time is my token holding time, and it is for this token holding time that you can actually transmit your asynchronous frames. So, this is how the amount of data that can be transmitted is determined in the FDDI network. So, let me just do a quick calculation on this. So, suppose let us say for instance I have a TTRT of 100 milliseconds, just some arbitrary number, okay, and my TRT happened to be 80 milliseconds and SA happened to be 10 milliseconds. So, look at what happens now. 80 plus 10, 90 milliseconds is my TRT plus SA. Target token rotation time was 100 milliseconds. Therefore, I have a 10 millisecond slack which is available. So, my THT will be set to a value of 10 milliseconds and I can transmit asynchronous data for a duration of 10 milliseconds. So, this is how we determine how much of data can be transmitted in when each time that the node gets the token. So, to summarize, what we have looked at in this session is the details of the FDDI protocol. Of course, we started with the idea of sharing using a token, then we looked at the frame format of FDDI, we looked at the choice of early token release, which is what is used in FDDI, and we looked at how we have two classes of traffic, synchronous and asynchronous traffic, which are supported on FDDI. And as we have been looking at FDDI, we also contrasted it with the 802.5 protocol. So, these are the things that we have looked at today. A few questions for you to review what has been done today. So, how is the FDDI network different from the 802.5 network? Now, this is actually a large question because many of the points that we have looked at will actually get covered in this question, but if you can at least identify the key features, that will be a good review. What are the fields in the FDDI frame? Third, why is a dual ring used in FDDI? Fourth, how is traffic classified in FDDI? 5, what is meant by asynchronous traffic? 6, how much of synchronous traffic can be transmitted by a node? So, if you are able to answer these questions, I think you will have a good review of what we have learned today in the FDDI protocol. Thank you.